So now that we've set up our sort of framework for how we're going to work with vectors, now let's start talking about the particular vector problems that we're going to end up spending a lot of time solving in this class. So for starters, we're going to start in a space that's called kinematics. So this is a branch of the subfield within physics that we call mechanics that's concerned with the motion of objects, where we're not at the moment worried about the forces or the torques that affect that motion. We're simply interested in how objects are moving. So there are several ways that we can describe an object's motion. So we can describe it in words, right? An object is moving 10 meters per second due east, right? We can use diagrams to draw pictures to show how an object's moving. We can use graphs. So again, we can graph an object's motion as a function of time, as a function of position, and then we can interpret those graphs. We're going to do a lot where we convert those first three types of representations into equations. So we can, given some assumptions about an object's motion, maybe it's moving at constant velocity, maybe it's moving with constant acceleration, maybe we're only interested in how it's moving between 2 points in time, but we're going to be able to come up with an equation to then go calculate what's going on. And then once we calculate what's going on, we're going to be able to describe the object's motion in terms of numbers, right? So here's our 10 meters per second as a speed, right? So it's got both a number, 10, a units meters per second, and it's describing how fast an object is moving. So all that is stuff that we want to get comfortable with in terms of thinking about the motion of an object. So for starters, let's think about sort of an object moving around in a nice two-dimensional space. And so what are relevant questions? Well, the first one that we can ask is, how do we describe where an object is located? And so if I take my object and just put it somewhere over here on the positive x-axis, I want to know where it's located. Well, what I'm interested in figuring out then is the object's position. We're going to use the vector r to represent the position of an object. That's going to be a vector that runs from the origin to the object's location. So again, I need to pick a coordinate system so that I know where the origin of my coordinate system is. Then I can draw the vector that runs from the origin to where the object is. That's going to give me its position. The position vector has dimensions of length, and so the SI unit that we're going to use to describe position is going to be meters. Now, my object can move, right? The whole point of this is that we're interested in describing an object's motion. So maybe it is at some initial position over on the positive x-axis, and at some later time, it's at some final position over here in the second quadrant. And so notice what I've got is two different vectors, one showing me the initial position of the object, one showing me the final position of the object. And so I can sort of track my object's position as it moves, and just that vector is going to change as my object moves around. So how do we describe how an object has moved? One way to do that is to talk about the displacement. So displacement literally just means the change in position. It's just another word we use to talk about the change in position. And so change in position, just like with any sort of change in quantity, is literally just final minus initial. So the displacement as the change in position just means the final position minus the initial position. That happens to be a vector subtraction problem. In terms of graphically, what the displacement or the change in position vector is trying to tell you is basically, well, where was the object and where did it end up? So it's a vector that runs from the object's initial position to the object's final position. Again, because we're still dealing with positions, the displacement vector has dimensions of length, and again, we're going to use the SI unit of meters to talk about the displacement. Now, if you want to talk about how far an object is traveled, that can be a different question, right? So notice that now I can have a way that my object moves where what I'm interested in keeping track of is the distance. The distance is a scalar quantity. It still has dimensions of length. We're still going to use the SI unit of meter, but the distance and the displacement do not have to be the same thing. They can be. So if my object follows a path that goes straight from its initial position to its final position, then what you'll notice is the magnitude of the displacement vector is equal to the distance that the object traveled. However, if my object follows some different path, again, the displacement is the same. Started at the same point, finished at the same point. The distance it traveled in going from initial to final is not. So the displacement only cares about where you start and where you finish. The distance cares about the path you took. So how did you get from where you started to where you finished? And so that the scalar nature of the distance says it doesn't matter to me which direction you're walking in. I just want to count up all the steps you took, no matter what direction. So that's the fundamental difference between distance and displacement. Now, we might be also be interested in keeping track of not just where the object is, but how fast it is traveling. And so let's start by thinking about how we describe how fast an object is traveling and what direction it's moving in. So again, there's sort of that additional piece of information that we want to keep track of here. That's the velocity. So the velocity, again, it's a vector. We're going to tend to use v to talk about the velocity vector when we label it. How fast and in what direction the object's moving is what the velocity vector tells us. The magnitude of the velocity vector is going to be equal to the speed the object is traveling, and the velocity vector points in the direction that the object is traveling, at least in terms of the instantaneous velocity vector. Its dimensions are now length per time. So now do I not only care how far you're traveling, but how long it takes you to travel that distance. And so the SI unit for velocity is meters per second. So our object, again, let's assume it's traveling on this sort of circular path, or curvilinear path is a technical term we might use to describe it. There's a velocity vector initially. So at that initial point in time, when it was over there on the positive x-axis, it was traveling in the direction indicated by the velocity vector, by the initial velocity vector, and at some speed. So the length of that velocity vector is telling me how fast it was traveling at that point. When I look at the final position, again at that final instant, not only is there a final position vector, but there's also a final velocity vector. It tells me that now my object is moving in this direction, so sort of up and to the right, given the way this plot looks. And again, it's traveling at some speed. Now you'll notice the magnitude of the final velocity vector is shorter than the magnitude of the initial velocity vector. That tells me that my object was traveling slower at that final instant of time than it was in the initial instant. So that's how I want to interpret that magnitude, right? It's telling me about the speed that the object is traveling. Now, if I just want to talk about how fast an object is moving, again, that was one of those two pieces of information, and that's the speed, right? So we will tend to use v without the vector symbol to talk about the instantaneous speed. It is a scalar. Again, it doesn't care about direction. It just cares that you were traveling at 10 meters per second, not 10 meters per second in a particular direction. Same dimensions as the velocity, still length per time, same SI units, meters per second. But again, the speed is just the scalar quantity that tells you how fast. When I add a direction, now I'm talking about the velocity. So we might also be interested in how the object's velocity is changing. That's the acceleration. So again, we're typically going to label that with a lowercase a. The acceleration is defined to tell us how the object's velocity is changing with respect to time. Again, it's a vector. And what we'll pay attention to is that there are three ways that we can change the velocity vector. You can speed up, you can slow down, or you can change directions. So again, speeding up means that you're going to make the velocity vector longer. Slow down says you're going to make the velocity vector shorter. So speed up and slow down change the magnitude. Because velocity is a vector, whether I change the magnitude or not, I change the velocity vector by changing its direction. So all three of those are ways in which you can change the velocity vector, which means all three of those are ways that an object accelerates. The dimensions for acceleration are length per time squared. So length per time per time. And so the SI unit that we will most often use for acceleration is meters per second squared. So again, maybe at our initial instant, not only do we have a position vector that we can use to describe our object and its motion, We have a velocity vector that's telling us how fast and in what direction it's traveling, and then we have an acceleration vector that tells us how that velocity vector is changing. Same thing at our final velocity, at our final position, or our final instant in time. There's a position vector that tells us where the object is located, a velocity vector that tells us how fast the object is moving and in what direction, and then there's an acceleration vector that tells us how much that velocity vector is changing. And what we'll learn to do is to interpret how the relative direction between the velocity and the acceleration vector really gives me the good description about how an object's motion is changing.